Okay, my dear students, in today's lecture, which is in fact a supplement lecture to the previous lecture, in which we discussed about the solution of the non-homogeneous differential equation. In fact, we discussed a technique known as the variation of parameters. Now that was the one of the techniques. There are several other techniques to solve non-homogeneous differential equations. We will go through few of these techniques during the course of our study. Let me give you very briefly another technique which is known as the solution of differential equation using Green's functions. So this is the Green's function method, as you can see before you. Don't worry about these page numbers, but you must keep the sequence as I have presented during my lectures. Okay, what is a Green's function? Green's function is defined for a differential equation, and the standard form of the differential equation, non-homogeneous differential equation, is y double dash plus pxy dash plus qxy is equal to fx. So we have this term on the right hand side, which is in fact the source term, which is called the source term as I told you in my previous lecture. Now the corresponding homogeneous equation, we will put fx is equal to 0, and we have learned to calculate the two solutions. The two solutions of the homogeneous part of this equation, y1x and y2x, should be linearly independent solutions, and then once we have these solutions, then we define the Green's function. Now this is the definition of the Green's function I am going to present, represented by capital GXP. So Green's function is a function of our old variable x and a new variable p, and is defined as the determinant of y1p, y2p, y1x, y2x divided by WP, where WP is the Wronskian of the differential equation with x is equal to p. So this is how the Green's function is defined, and in following this we have calculated the Green's function for few of the differential equations. But once you find this Green's function, you can write the solution of the non-homogeneous part, that is the particular integral, which is ypx, as the integral upper limit x gxp fp dp. So you must remember these two formulae. One is the solution and the other is the previous equation as defined by Green's function. So this is how the solution is written for a non-homogeneous differential equation using the Green's function method. Now the logic for the Green's function method and the derivation of this formula is not in the scope of your course, but if you go for MPhil or higher classes, you will discuss and derive this formula. So we are not interested in the derivation of this formula, but we will use this formula as we will use it in this example. This is a differential equation y double dash plus y is equal to sine t with the boundary conditions as written here. Now the corresponding homogeneous differential equation is y dash plus y is equal to 0, as this is a differential equation with constant coefficients. So we do not need to go for the Frobenius method, but we will write the characteristic equation of this equation, which is m square plus 1 is equal to 0, and from here there are two roots of m is equal to plus minus iota, and we jump to the solutions of the differential equation, homogeneous differential equation, which is a1 e to the power ix plus a2 e to the power minus iota x, which is simplified to the constant c1 cos x plus c2 sin x. And after we find the solutions y1 and y2, as y1 equal to cos x, y2 is equal to sin x, we can now find the Green's function of the differential equation as defined above: gxp y1p y2p y1x y2x divided by y1p y2p y1 dash p and y2 dash p. So when we substitute the values of y1 as cos p, y1p, and we get this equation, and when we simplify and calculate this determinant, we see that the Green's function of our differential equation comes out to be sin x minus p. So once you find the Green's function, you can write the solution yp is equal to gxp fp dp, and this is you put the value of sin xp as this, you put the value of f of p as sin p and dp, and you can immediately write the solution of this differential equation, the non-homogeneous part of this differential equation. So this is how the Green's function method is used to find the solution of the non-homogeneous differential equations. Okay, let me now discuss a particular example in which you will learn few useful techniques. Now this is the equation we want to solve: t square y double dot plus 7t y dot plus 5y is equal to t. So here our independent variable t is t using Green's function method. So these are the boundary conditions, and we will write our equation as the homogeneous part of this equation as t square y double dash plus 7t y dash minus 5y is equal to 0. So I have replaced dots with derivatives, dashes. It does not make any difference. So we change the independent variable from t. So now let us introduce another variable z instead of t. So t is equal to e to the power z, z is equal to log t, and when we substitute the values of this t, we get, this is the derivative with respect to z, and we define capital D as the derivative with respect to our new variable, and the derivative of y with respect to the old variable using the chain rule will be dy over dz into dz over dt, and when we write the value of dz over dt as determined from this equation, we get dy by dt is equal to 1 over t capital dy, which leads this equal to capital dy is equal to py dash. And similarly the second derivative is obtained, and we substitute the value of the first derivative in the new variable and the second derivative in the new variable, and when we do, you go through these steps here to see that t square y double dash, the first term of this equation, becomes equal to t into d minus y. Similarly, the second term is obtained as 7d, and the third term remains as 5y. So when we substitute our new variable into the given differential equation, the differential equation reduces to this. Now this next page is not very clear, but let me give you a clear addition of this page. so you can see this page over here. I'm sorry, not this one, but there is another page. Let me bring that page from the notes. Okay, this is the page I was looking for. Let me show you this page. Right, this is the page. So we will continue with y1 writing e to the power minus 5z and y2 e to the power minus z, and we now substitute our original variable instead of z to get y1t as e to the power minus 5 log t is equal to 1 over t5. Similarly, y2t becomes 1 over t, and now we find the Green's function which you can follow from these steps, and the Green's function comes out to be this one, and we substitute the value of Green's function in the formula over here to get the solution of this differential equation. So why in particular I have discussed this differential equation? The reason is that this differential equation, as it was given original, we see that this is not the differential equation with constant coefficients. Okay, as you can see, the coefficients are not constant, but they are variable, they are polynomials. But by doing this transformation from the independent variable z to the variable, from the independent variable t to the variable z using this equation, we have transformed this equation into this equation, and you see that this equation, you can say it is a equation with constant coefficients. So that's why we have written this solution. So that was the purpose of introducing this particular example, that sometimes you can convert a differential equation with variable or polynomial constant polynomial coefficients into a differential equation with constant coefficients. So I think that's all for this supplementary lecture to the previous one. And now as I discussed the exercises and the homework in the previous lecture, you must go through this and complete this chapter. Okay, thank you very much.